Morning, everyone. Um, I have been talking about this in past years, but we actually intensified this research a lot over the last year. Essentially, we're trying to do the impossible, which is redesign the current internet and try to come up with a new basic point-to-point communication architecture that would actually replace BGP in today's internet. And obviously, why should you sit here and not just run out and grab coffee? Let me try to tell you some of the reasons why we've actually intensified this research. And right now, a lot of people are working on this project, including Subham Lee, who's a Scilab systems scientist, Shuqun Xiao, a PhD student, Hyunjin Kim, who just graduated a week ago with her PhD thesis, Yusun Lin, who's a postdoc, Songjae Yu, who's a master's student who has done a lot of the programming, and Virgil Gligor, who everybody knows. And in the past, Xin Zhang, Jeff Asker, Hawan Chan were students who worked on the project, and David Anderson, maybe some of you also recognize as a faculty in computer science and networking. So again, why would we even consider changing today's internet? Because for all practical reasons, there's a lot of deployed infrastructure and everybody knows it well, so it's almost impossible, it seems, to deploy a new network. However, over the last few years while we worked on this, I believe there's some real reasons why this actually has a chance for seeing the light of day. So first of all, the obvious reasons are the current internet was not designed with security in mind, although even in the 70s people have thought about attacks, but simply creating a network that is functional was by far the major concern, and so security was not really considered initially. Recently, though, we've seen a lot of attacks, and we've seen these attacks for over a decade. In fact, just last week we had attacks on some major US banks that prevented customers from accessing those websites. And a lot of these attacks, you could say, well, they're availability attacks, but during the lecture last Friday, my TA was suddenly raising his hand, and when we talked about this in class, and he said when he tried to log into PNC, it actually took his HTTPS connection back to an HTTP connection, and his account information was being displayed. So somehow, even though there was a denial of service attack going on, the web server made a mistake and somehow was overwhelmed and redisplayed his current HTTPS connection as an HTTP connection, which would allow anyone to inject commands or see his account information. So we've also seen prefix hijacking of IP address spaces, which is very frequent. For example, last year, the US military's address space was hijacked by an ISP in China, and all the US military traffic was rerouted through China for 20 minutes. So that's pretty serious. There's also been DNS spoofing where large address spaces, traffic for large address spaces were redirected to foreign places. So these attacks are actually quite frequent. So yesterday there was another attack that's not directly an internet attack, but that just displays that we do have an issue, which was at the White House. There was a spear phishing attack where people have sent bogus emails, very targeted bogus emails to White House staffers, and they clicked on those links, and their computers got compromised as a consequence. You could say that isn't directly a network security issue. However, a lot of the tools that we're going to show can actually help preventing these types of attacks. So you could say, well, we have BGPsec, we have DNSSEC, it's going to solve all our problems. The issue, though, is that a lot of these new mechanisms also introduce new problems. Like BGPsec keeps having several convergence issues, and route flap dampening also introduces new attacks. So if you don't know about this, don't worry. These are newer protocols that have been designed. But again, I'll be happy to walk you through the issues that they introduce. Another major issue we've recently realized is that there are several circular dependencies with respect to authenticating internet messages and having routes to other certain servers. So for example, in BGP-SEC, when you receive a BGP message, you have to go and contact yet another server to download the information to verify that message. Right? So now you ask yourself, well, how can this be rebootable? How can you reach a remote server if you can't even find a path yet to that server? Right? The BGP protocol helps you find paths. So in order to verify those messages, routing has to work, but you cannot route unless you can verify these messages. So we found this, and again and again and again, people keep saying, well, we've solved all the problems. Look, here's this new protocol, but then they don't realize that these new protocols introduce new issues. Another major issue that has seen not a single solution so far is a single root of trust problem. In today's internet, we keep seeing new solutions that require a single root of trust, right? Where one entity in the world has some private key, and with that private key, you can influence the entire operation worldwide. And so it's easy to say, well, that's a great solution if you're the holder of that single key. But in all other cases, right, having the world agree on a common root of trust is a very challenging problem. So, of course, we also need high availability and assurance. And the observation that I've made is that if you really want a new major property to be deployed and to really drive deployment, you really have to have a major advantage that can get you over the additional effort required to deploy this and to achieve this advantage. So, for example, who would have thought a few years ago that 80-year-old people would learn an iPad and start using an iPad on a daily basis? Right? People perceive an advantage of using a device like an iPad, and they overcome the effort in learning it in order to use it. So if you really have a major advantage, people will overcome the difficulties in deploying this new device or technology. Another example is IPv6. So people always say, see, we couldn't really deploy IPv6, so therefore, how are we going to deploy a new internet? But if you think about IPv6, the advantages were really very minor. It required a lot of changes, but you couldn't really get major benefits from deploying IPv6. And so that's the observation here. We really have to have some very major advantages. And the major advantages I'm talking about here are advantages like guaranteed availability or path validation or low energy, etc. So truly major advantages that would simply prevent all these previous attacks that we've witnessed. So in this new internet architecture that we're working on, we're trying to provide exactly these very major advantages that we don't have today. So for example, have very high availability, even in networks with malicious parties. And in many cases, we can even provide guaranteed availability even if you're under a denial of service attack. You also want explicit trust for your network operations. So you can have a very simple rule that says this traffic should stay within the US military network, for example, or this traffic should stay within the US. And therefore, if anyone tries to redirect your traffic through another country, it's going to be immediately obvious because you know precisely which entities your packets will flow through, and there's simply no way in which somebody can redirect your traffic without you noticing it. You also want to have a minimal trusted computing base so that you don't have to trust the whole internet to achieve your security properties, and also operate without a single root of trust in a network with mutually distrusting entities. So more at the networking level, you also want to have balanced route control, so a receiver can influence the path as well as the sender can influence the path, and also avoid the circular dependencies. So, and finally, we don't want to pay anything for this. Ideally, this new architecture should be more efficient than even today's internet. So here's a brief overview of the basic architecture that we're working on. And I know some of you have seen this, but I'll keep this to a minimum. And then to a minimum to understand the properties we can achieve. So at the major level, we split up the world into different trust domains, where each trust domain is an entity or an area where everyone can agree on a uniform root of trust. So for example, the US would be one of these trust domains. Europe could be a trust domain, or different countries can form their own trust domains. And these trust domains will give you isolation as well as a little bit of scalability. However, the major scalability does not come from this decomposition. The nice thing about these trust domains is that you get this property called enforceable accountability. A lot of people today say if we only had accountability in today's internet, all our problems would be solved. Because let's say someone attacks us, so we can go and prevent that attack because that person is held accountable to their actions. Although the observation we've had is that accountability doesn't give you anything unless you have enforceable accountability, right? If somebody from Russia is attacking you, what are you going to do, right? That accountability does not give you anything. Accountability only gives you power, a powerful property, if you can do something about it, if that accountability is enforceable. So specifically, if someone in the US were to attack you, you could do something about it, right? You're within the same legal framework, within the same jurisdiction, so you could actually pick up the phone and do something about that attack, or contact the trust domain core and say, look, this person is attacking me, here's the evidence. And within a trust domain, you can do something about it. But if someone in Brazil attacks you, unless you are fluent in Portuguese, there's really not much you can do. So probably even if you're fluent in Portuguese, there's not much you can do. So these trust domains actually really help in many ways, because each trust domain is going to have their own root of trust that everyone can agree to. Next, we have a very different way to construct paths, and this trust domain core issues a set of what we call path construction beacons, and this is essentially a network flood that traces paths back to the trust domain core. So after this process, each destination will obtain a set of paths to reach the trust domain core. And after this flood, everyone can already communicate with the trust domain core. So it's a very simple operation, and within a single flood, the whole network learns about these paths. So at this point now, every destination or every autonomous domain uploads under which paths they want to be reached. So there would be a DNS type system in the trust domain core that stores the paths under which somebody wants to be reached. And so if, for example, this blue source wants to communicate with the red destination, it downloads the paths that this red destination announced through a DNS type system, and then can form an intersection intersecting its own paths with the paths of the destination, and then finding a shortcut that leads directly to the destination. So several observations here. These paths are actually embedded in packets. So the packet will carry the information at the ISP level, how it gets from the source to the destination. So the source actually has a lot of choices and can select which paths it wants to pick. So this very simple protocol has a lot of nice properties that we wanted to achieve. The first one was explicit trust. The source knows exactly whom it has to trust for the packet to reach a destination, right? You know precisely which ISPs will be traversed to reach that destination. So this attack of China hijacking the US address space could have been trivially prevented by saying, having a firewall rule that says only permit paths that stay within the US trust domain. Or you could have a rule that says, we actually support sub-trust domains, so these are hierarchies. So the US trust domain would contain a military trust domain, which would itself contain a trust domain that has highly secretive information. And so you can have very simple rules that specify, do not allow this packet to leave this specific sub-trust domain, and the network will enforce this property. Another property was this path choice by receivers and senders. So the receivers can select how they want to be reached, and the senders then can compose their own paths with the receiver's paths. So you get route control by ISPs, you get route control by receivers, and you get route control by senders in a very scalable fashion. In terms of efficiency properties, this protocol is almost infinitely scalable because there is only a single flood that traverses the network. In today's internet, you have the current BGP protocol is actually not scalable the way it's built because every single destination floods the whole network. Right? So if you were to scale the network up, because every destination floods the network, each link will carry as many route updates as you have destinations. Especially with BGP-SEC, because in BGP-SEC you cannot aggregate path announcements anymore, and therefore BGP-SEC really prevents scalability of today's BGP. But in this network, instead of having one message for each destination, you have only essentially one message period that is being traversed during this flooding stage, or a very small number of messages, like 5. So it scales much better. Routers also become massively simpler. In this architecture, a router does not need a routing table anymore. You may think this is routing tables are not a problem, but if you ask ISPs today, what is one of the biggest issues you're facing today? It's that routing tables keep getting bigger. So you say, well, memory is not a problem, right? How big can they be, right? That's not a big issue. However, remember that the routing table performs a very complicated operation, which is called maximum prefix matching, which means that the entry that has the longest match is the entry that's going to be selected. And this is a big problem if you try to do this within a few nanoseconds. And current routers have special devices called TCAMs, ternary content addressable memories, that perform this matching very efficiently. Now the problem with TCAMs is they're very power hungry. For each megabyte of storage, they burn 15 watts of power. So now you say, all right, so let's just have a bigger routing table. Essentially, your data center is going to overheat if you try to do that, because you're trying to pack as many routers as possible into these data centers. So it turns out we're really facing a lot of these types of issues with the current architecture, and with what I'm proposing here, this makes much simpler routers that are a lot less memory or power hungry, that by preventing these routing tables, right? There are no more routing tables. Packets contain this information, and it turns out you can verify information in packet headers much faster than you can do these TCAM lookups for large TCAMs. So I could go on for another hour and tell you more reasons why this is useful. I think I'm already 6 minutes over time, and I would like to enable some questions. However, let me maybe not go through the crypto. Let me show you how this would actually look like in the real world. So you would have multiple trust domains in the world with different trust domain cores. You can have peering links with different trust domains. So your packets could traverse these peering links without going through your trust domain core. But the point is, you always have full visibility of what is happening to your packets, right? So whenever you would make a traverse a peering link, you would see that as a sender, and you know exactly, all right, so now my packet is actually going to Europe, or now it's going to Russia. And we've actually built this whole architecture. So I'm going to briefly show you the packet header, but I'll be happy to also walk you through the advantages as well as disadvantages of this protocol. But some of the main advantages are these cryptographic validation of forwarding information. So essentially your packet cannot go across a different path than what you're expecting it to go across. You have trust agility, so you can locally know precisely whom you have to trust and select whom you have to trust for network operations. As a consequence, we believe we're going to achieve much, much higher reliability and at least 1 to 2 additional nines of availability. The current internet has about 3 to 4 nines of availability and the telephone network had 5. So we would like to get much closer to the type of reliability and availability that the telephone network had. And we believe with this architecture, we can actually achieve this. One main reason is the decomposition of, or the partition of the data plane and the control plane. Right? If you have a path, somebody can still attack your routing protocol, but your path continues to work. Right? That's a very powerful property. In today's internet, you can never achieve strong assurance for your traffic, because even if you currently have a connection open and you're doing telemedicine, telesurgery, or some highly important procedure, somebody could attack the routing protocol and you would lose your current connection. Right? That is, it's impossible in today's internet to get really high assurance because of for every packet you send, the routing table is being considered. And so if somebody attacks the routing protocol that changes the routing table, your current traffic simply cannot get to the destination. And so these are some really powerful properties that this new architecture provides. And in addition, we believe that we can even be more efficient and faster than the current IP switching, IP forwarding. So there are also some disadvantages I should mention. There's one point that is not as scalable, not perfectly scalable, which is when destinations learn their paths, they have to keep updating the DNS system. And that's one point where we have, again, some non-scalability, because every destination, every few hours, has to keep uploading a new path. Now, this is not a flood. This is a unicast message. And so we still believe that this network is still highly scalable as a consequence, because the information is really tiny, only a few kilobytes that have to be uploaded to a single destination, not like in today's internet, where every destination has to flood the entire internet with routing updates. So there are also new protocols, new equipment that's obviously requires a huge burden to change some of the routers. However, we believe it's a very small amount of equipment that has to be changed. The majority of all switches in networks can still remain the same switches though. The static path binding, a lot of people perceive this as disadvantage because they love the fact that the current internet, if there is a problem, somehow the internet will find a new path. Now, that's exactly the reason why you can never achieve high availability or high assurance. And so we believe that this is actually a major advantage of having this static path binding and being able to reroute yourself if you notice that there's a failure or flaw or fault with a given path. So let me mention a few advantages and disadvantages for major stakeholders. So for manufacturers, they could actually sell new equipment, but for current major router manufacturers, this could actually be an issue because the routers become much more simpler and easier to build in this new architecture. So some of the current router vendors may not be too happy with this because if anyone can build highly efficient routers, it's not going to be to their benefit potentially. It's going to squeeze margins and have a lot of new players in this marketplace. For ISPs, though, there are a lot of advantages. So there are new revenue streams they can obtain because now they can actually sell high availability. Right? You could say, well, we had QoS over the last decade and it never happened. Well, the reason was because you could never achieve strong properties for your quality of service. Right? An ISP could never, if they were to sell quality of service, they actually had to provide true guarantees. But there were no true guarantees because it was still vulnerable to attacks. And so I believe if we actually have a network that provides strong availability, even in the face of attacks, there are actually new powerful properties that can be provided as a consequence. Like these distributed denial of service defenses that actually work in the network. And so the incremental update actually is also, I believe, an advantage because the routers hopefully will be relatively inexpensive and only the edge routers have to be changed. So inside your core, nothing has to change within an ISP. But of course, they have to purchase new equipment, new protocols, train their system administrators. That will be a high overhead. In terms of consumers, they would need to perform a software update, potentially even upgrade some hardware, but hopefully the differentiated services for people who want high availability will provide as a major benefit to overcome the drawbacks. I think for governments, I see almost only advantages. First of all, for example, if you have a service like Smart Grid, you really want high availability for your smart grid communication. The selectable roots of trust and no single global root of trust, I think, are also an advantage for many governments, as well as simple and verifiable router hardware. We're seeing, when I travel throughout the world and I talk to people, one of the single biggest concerns is the malware in different routers, right? So for example, Huawei routers are deployed throughout the world, and everybody is worried about malware and backdoors in those routers. Companies still keep buying them because they're quite inexpensive, so they're already deployed in large quantities, but modern routers have tens of millions of lines of code. And so validating that this code is correct and doesn't contain a backdoor is nearly impossible. And of course, the backdoor could also be in hardware as well. And the point here is that in the SIAN architecture, the routers become much, much simpler. That can actually enable validation and verification that is much easier than in current protocols. All right, so let me stop here to enable some questions. But if people are interested, I'd be happy to go through the incremental deployment with you and show what has to change and walk you through the new packet headers that we have and through the new properties that we can provide. So in summary, you can see this. Hopefully you see that there is some hope that we have some new networks in the foreseeable future. And this is just one effort that we have here in this space. There's a very large project called the XIA project. We're here at CMU that also looks at a future internet architecture. However, XIA is based on the SIAN network for the basic forwarding, and XIA is an overlay providing additional flexibility, like providing easy ways to download videos and movies, which is also important to achieve good scalability. All right, so.